Hello and welcome. My name is Joshua Gould. This presentation and project prototype is entitled AI-nimation. The initial research was done on behalf of the Digital Media Innovation course at the Rutgers School of Communication and Information as a part of the graduate program in Media and Communication. As a quick synopsis, this presentation focuses on the theoretical ability of machines to demonstrate computational creativity and presents a prototype for a hypothetical platform. Also note, this is a video version of an interactive presentation. You can find that URL listed in the description of this video below. The video that follows does not allow for hyperlink citations, which you may see at times, and also includes footage that I do not own, but all will be referenced and cited at the end of the video. Also, this is not monetized and is strictly being used for educational purposes. Can machines interpret art? Can they learn to create art? The goal of this presentation is to conceptualize my prototype, and this requires a brief overview of artificial intelligence, its influence in the creation of digital media and art currently, and what the hypothetical applications and audiences would be. Hopefully, by examining contemporary arts projects powered by artificial intelligence, you will be convinced the science behind this prototype can be achieved. First, we will take a look at the prototype concept. On the next slide, you'll watch a 1-minute video on a speculative advertisement based on my innovation. The prototype relies heavily on emergent technology in the artificial intelligence sector, and for this reason, it's very important to revisit some key concepts and a brief history of AI itself. By then closely examining creative projects using artificial intelligence for the arts, we can extrapolate a better abstraction of what computational creativity looks like today. Hoping to truly conceptualize this prototype, we will then outline the science and resources needed to develop and launch AI-nimation. Finally, we will address the desired uses and markets for this innovation.
Artificial intelligence has unlocked new paths to creativity. AI-nimation empowers users to turn plain text into seamless animation in just seconds. The process is simple. Describe or caption a scene in your own words, and our advanced algorithms will identify characters, settings, objects, behaviors, and actions. After the information is processed, AI-nimation renders a vibrant, universal animation. AI helps make sense of big data, it allows cars to drive themselves, and now we're bridging the gap between human creativity and machine learning. AI-nimation, where computation meets imagination.
Let's take a moment and break down the very basics of this prototype's features in the video we just saw. First, AI-nimation scans text. It looks for keywords and scene descriptors, like characters, props, behaviors, locations, etc. This is achieved through character recognition, which we will discuss shortly. From there, the neural networks sort and pair data. They retrieve this from video databases and also compensate with procedural pixel generation, matching our words to visual images. Finally, it renders animated scenes, compositional representations of the text retrieval through a fusion network. I know it sounds like science fiction, computers turning plain text into animations instantly, but my research findings posit work being done today that actualizes this idea. However, before we can get into the science behind this theory, we will gloss over some brief AI terminology and history. So, what is artificial intelligence? It's the idea or act of imbuing machines with intelligence, the goal of emulating a human being's unique reasoning faculties. This includes perceiving the environment, learning from past data, taking action, and achieving goals. Sometimes called computational intelligence or the design of intelligent agents, neural networks, genetic programming, computer vision, heuristic search, knowledge representation and reasoning, language understanding, all of these are revealed through the growing capabilities of intelligent agents. There is also an honorable mention here of Nils John Nilsson, an American computer scientist, and he is regarded as one of the founding researchers in the discipline of artificial intelligence. Now let's take a quick glance at the history of AI. The term was first coined in 1956 when philosophers and logic theorists like John McCarthy attempted to make sense of human thinking in the context of a system, and this idea resulted in the coinage of the term. In addition to the timeline that shows key developments through the decades, we should also mention noteworthy inventors like Ray Kurzweil with his developments in text-to-speech and speech recognition, Marvin Minsky, who is the founder of the MIT lab and was also considered one of the greatest minds in computational science, and Geoffrey Hinton, the godfather of deep learning networks. The timeline shown here may not explicitly demonstrate how computing technology moves so fast, but just consider that machines that today calculate basic functions or even recognize text are no longer considered AI. Instead, they are inherent computer functions. When we discuss artificial intelligence, it's important to learn some of the key components and terminology behind AI. Machine learning, which is a common term, refers to the ability for an algorithm to learn from prior data in order to produce a new behavior. Examples even spill into medical applications today, analyzing large genome sets in an effort to prevent diseases, diagnosing depression based on speech patterns, and even helping to identify people with suicidal tendencies. Deep learning, another common term, is a branch of machine learning, where artificial neural networks, which are algorithms inspired by the way neurons work in the brain, find patterns in raw data by combining multiple layers of artificial neurons. Finally, algorithms, which is of course a buzzword, at their most basic form, simply tells a computer what to do next with an and or not statement. Think of it like math. It starts off pretty simple, but becomes infinitely complex when expanded. These algorithms help to highlight patterns and matrices in complex data sets and can do fascinating things. Computers have always been a creative tool, but advances in artificial intelligence could make it a creative entity in its own right. Computational creativity is a term we use when computer programs replicate aspects of certain creative behavior. The so-called Turing test measures the ability of a computer to convince a person communicating with it that they are actually conversing with another human. And this has long been presumed the arbiter of machine intelligence. The Newcomb Institute for Computational Science at Dartmouth College reconfigured the Turing test for computational creativity, positing the question, can algorithms create human-quality short stories, sonnets, dance music sets, and other pieces of art? The competition is to determine whether people can distinguish between human and algorithmic creativity. The goal is not to replace human creativity, but to assess whether current computational technology can produce outputs that cannot be distinguished from it. Margaret Bowden has some interesting thoughts on the subject. She is an AI research professor and cognitive scientist, and she claims, quote, "The germ of our culture, all of our knowledge and our experience, is behind each creative idea," end quote. In other words, physical laws, theorems, musical pieces, these can all be generated from a finite set of existing elements. And therefore, creativity is an advanced form of problem solving that involves memory, analogy, learning, and reasoning under constraints, among others, and is therefore possible to replicate by means of computation. So when we return to one of the major questions of this prototype and presentation, can machines create art? First, we must answer, can they interpret and understand art? At the Art and Artificial Intelligence Lab at Rutgers University, machines are being programmed to try and understand art. Neural networks scan and evaluate over 80,000 digital paintings, and they're programmed to analyze key visual principles based off Henrik Wolfin's comparative approach to formal art analysis. In the next slide, you'll watch a short video about some of their findings and the science behind understanding art. When we look at pieces of art, like the Mona Lisa, what do we see? Computer scientists Ahmed Akmel and Babek Salah at Rutgers Arts and Artificial Intelligence Lab are programming a neural network to decipher and interpret art compositions. Algorithms are designed to analyze centuries of work within seconds. Some of the findings are truly surprising. For example, the Mona Lisa rated lower on its creativity scale than many of Da Vinci's other lesser-known paintings. The program was also able to discover links and parallels between compositions and artistic styles, even between two very different works of art, like this 1950 painting by Norman Rockwell and this 1870 painting by French Impressionist Frédéric Bazille. Here, another example, between this 1890 painting by Van Gogh and this 1922 farm scene by Miro.
The algorithms can actually flag very transitional points in art very correctly without any knowledge about the art at all. They didn't know anything about Picasso or Munch or Cézanne, but still recognize influential pieces of work in their career. So all these abilities involve perceptual, cognitive, and intellectual abilities when we look at art. We would like to really transfer these abilities to the machine, to really push the envelope of what we can do in computer vision and artificial intelligence.
In visual art, every single item has its own definition of beauty. And that's very clear to me that we need to understand this and analyze this and try to factorize it, actually. That's a very interesting to me and fascinating project to do.
Projects like this will often draw criticism, but should be regarded as additional means to understanding a topic better. These algorithms can potentially answer deeper questions about art, capable of quantifying and analyzing a ton of visual materials far better and more accurately than humans can. So it's quite possible we can program machines to analyze and interpret art, or at least data through art. But can they create entirely new compositions based on that data? The next Rembrandt is a fascinating example about how machines can not only understand art, but create new art based on prior data. ING and Microsoft's project, The Next Rembrandt, brings back to life one of the greatest masters, using advanced data recognition and state-of-the-art technology. Paired with experts in various fields, over 160,000 fragments from all of Rembrandt's 346 paintings were analyzed using 3D scans and digitized images upscaled by a deep learning algorithm. Then facial recognition software was designed to understand Rembrandt's style and generate brand new facial features using a height map to mimic Rembrandt's exact brushstrokes. Then physically brought to life using a 3D printer and 13 layers of paint. And so, 347 years after his death, a new Rembrandt made from data and machine learning alone was unveiled and exhibited in Amsterdam, raising the question, where can technology take us if it can truly create art? Google's Deep Dream project is a fascinating look at neural networks within computational creativity. It was programmed to identify shapes such as animals and landscapes within digitized photos, and generates its own images on top of those interpretations. So basically, we're looking at a visualization of what the computer sees or thinks it's seeing. In the next example, you'll watch a short video about how a common walk down a nature path can turn into something truly psychedelic when it's rendered through Google's Deep Dream. Although procedural generation isn't traditionally artificial intelligence, it's a way game developers can introduce carefully controlled elements of randomness into their work at inexhaustible quantities. Instead of molding and shaping each tiny nuance in a game, these developers can program certain parameters into a mathematical algorithm that generate endless amount of content itself. No Man's Sky, released in 2016, is a space exploration game with a vast galaxy. In fact, 18 quintillion planets, so large that someone could play the rest of their lives without stumbling upon a planet that another player has explored. In No Man's Sky, there is a near infinite procedural universe. This may seem impossible, but advanced computational math is key. Even here, at the galactic level, each light we see is a star with their own solar system and planets filled with life and ecology. Listen to founder and lead developer of Hello Games, Sean Murray, try and explain the process of rendering an entire universe.
If you imagine a sheet of graph paper, and it's like an infinitely scrolling sheet of graph paper, and we choose at random certain squares on that grid and just color them in. And those are our stars. So if you imagine that in 3D, and then you imagine it kind of warped by shapes and spirals and spheres and things like that, then it gives you these really pretty patterns, but it also gives you something quite realistic to our own kind of galaxy that we're in.
If a player wants to explore any system, they can land on a planet-sized planet, walk in any direction for weeks, experience actual day and night cycles in proportion to that system's sun. This isn't a level designed by artists. Everything you see is generated through algorithms: the terrain, the water, the trees, the foliage, and even life on the planet itself.
The terrain is being generated around me, and it's not just the terrain of this planet, but the terrain of, if you see other planets hanging on the skyline, on the horizon, those are generated in full too. As I fly towards them, or as I fly through the terrain that we're on here, it generates around you in higher and higher detail, kind of what we would call level of detail in games. Normally that would be created by an artist. For us, it's just created by maths.
No Man's Sky is a staggering example of world building and computational power, creating an entire universe from procedural algorithms. Certainly, this type of procedural design can be leveraged for simple pixel generation in visual compositions, like the ones theorized here. Our final example of computational creativity strays away from the aesthetic and visual. Here I wanted to provide another look into how artificial intelligence can skew the arts, not just visual compositions. Sony CSL Research Labs' Flow Machines analyzes and learns musical styles from a huge database of songs. It then autonomously composes original music based on that data, once again proving that existing art can be turned into computational objects to produce new art. In the next example, you'll listen to a short audio clip entitled Daddy's Car, a song entirely composed by artificial intelligence after scanning work from the Beatles. The lyrics may not make total sense in Daddy's Car, but there's no question that this composition has rhythm and artistic quality. So getting back to my prototype, and the idea that we can give a machine simple plain text and it can give us brand new animations based on that text. We can now ratify some of the science behind this. So first, it's a text input. This is simple character recognition, which is commonly found in most software today, and natural language processing. Nothing too advanced there. It then moves to the text detection. This is algorithmic pairing, where we pair the text with visuals and spatial data. This can be done from any amount of visual data sets or libraries. Essentially here, we're pairing words and descriptors with different visual elements, and this can all be done algorithmically. The last step is the compositional retrieval and fusion network. Sounds pretty fancy, but what that means is it's going to generate animations based on the algorithmic pairing. From there, anything it can't readily determine will be patchworked through procedural design and pixel generation. Further conceptualizing this tool, it starts simply with machine learning. Then it leverages algorithms and neural networks programmed to scan specific visual data, compositional retrieval and fusion networks to digitally create images, and again, the procedural design for patchwork and pixel generation. I encourage you to check out some of the references here. So to try and actualize AI-nimation, and serving as a brief outline of resources needed to bring AI-nimation from an idea to the marketplace, it requires 3 critical phases. First is pretty much theoretical, which we covered today. Interpreting and creating art is possible with today's technology through artificial intelligence. However, AI-nimation still would require some nuance, especially in regard to intersectionality with these existing tools, in order to achieve the desired function of turning text into animation instantly. The next step would be actual development. This would require recruiting developers specializing in artificial intelligence. There's no shortage in this field. Worldwide spending on cognitive and artificial intelligence systems will reach $19.1 billion according to the IDC this year. We could secure funding through grants, or we could also get partnerships or fellowships for initial research flight.
Test periods would have to preface any client-facing release, and in reality, the neural network could be trained to work off smaller data sets if we were working with a smaller timeline. AI-nimation's text-to-visualizations function would have an endless application in the marketplace. Education, especially mastery and distance learning, would benefit immensely from this type instructional tool. Animation, like iconography, is simple and universal, and therefore its utility for communication is widespread. We'll talk about some of the applications in a future slide. So what's the assessment plan if AI-nimation would go to market? Well, with any software or digital platform, testing would have to be a necessary step. This would reveal bugs in the code or program and ensure its quality. This way, we would increase customer satisfaction, which of course adds to profit and reputation. This testing can be done in-house, it can be outsourced to early adopters, or done collaboratively. Beta testing can also be done with each new product feature or patch created for the platform. This can be performed on closed test servers or to ensure a positive installment and product delivery. Next would be feedback, and here we'd look at key metrics and analytics that can help measure engagement, product reviews, customer feedback, tester feedback, etc., which all help and serve as performance indicators. Next would be the market itself, including market research. It is extremely important for building customer profiles to help determine where AI-nimation could reach targets and new demographics. Licensing protects the intellectual property. Non-disclosures for early employees and developers help confidentiality, especially in emergent technology where this can be a risk. Finally, sales is a huge part of any assessment, not only determining the price point for a product, but also seeing where we stand with the market and competition. I also propose a simplified version of AI-nimation could be released in a freemium capacity. Users can try a limited version of the program for free and pay an upcharge to unlock the full features of the product. Freemium is a common pricing strategy for digital offerings today and is wildly successful, especially among games. So what are the applications for AI-nimation? Walt Disney tells us that animation can explain whatever the mind of man can conceive. This facility makes it the most versatile and explicit means of communication yet devised for quick mass appreciation, end quote. So education, I think, would be the first and foremost and also the most valuable, as animation itself is an educational tool and has powerful means to improve understanding and the ability to perceive our world. Basic systems and mastery learning all benefit from animation. Previously, traditional animation required specialized, labor-intensive techniques that were both time-consuming and expensive. In contrast, software is now available that makes it possible for individual educators to author their own animations without the need for specialized experts. Teachers are no longer limited to relying on static graphics, but can readily convert them into educational animations instantly with this hypothetical tool. The next application is, of course, communication, as animation is a powerful communication tool. It has the ability to capture an audience's attention where other methods may fail. It can be memorable, enduring, endearing. It can inform, narrate, instruct, or explain. And overall, animation has the potential to build up an emotional connection and empathy that other mediums might not have. Lastly, entertainment is, of course, a primary form of using animation, as its first aim was to be used in movies, cartoons, or short videos, so that sector has endless applications for AI-nimation. Finally, during my research, I also looked at any sort of competing media or competition in the marketplace, and I was only pressed to find one. It's entitled Plotagon, and it's a software that was originally developed for screenwriting that's now been merged with 3D animation capability. So as you type actions, lines, and settings for your characters, those characters will actually play out your visions on screen, complete with auto-directed cuts. Now, this may seem similar, however, the script interface is very rigid and it still demands more of a learning curve than AI-nimation would simply entering plain text. It also is more of a sandbox tool in terms of the animator. You're still in control of facial features, you can move around the background, there's more customization, whereas AI-nimation would be in the driver's seat for most of the animating. Powtoons is another example here, but that's just template-based and is used in the educational sector. It's intuitive animation software and leverages a library of styles, characters, backgrounds, and video, but again doesn't have any functions similar to what's proposed here. Thank you for watching. This is the end of my presentation and prototype example. I hope I inspired you to think that artificial intelligence is capable of not only understanding art, but possibly even generating art discernible from our own. This tool, again, was just hypothetically conceived as a part of a class project for digital media innovation, and I'd be happy to answer any and all questions. You can shoot me an email, And you can advance the slides or stay on the video here for all of the references and research used. Thank you.